What's up, everybody? We're going to have a little car race between this blue beat up remote control car and this little remote control car. And the thing about it is, we've already calculated their velocities. The blue car, its velocity is 1.82 meters per second, and the white car has a velocity of 1.58 meters per second. And we are going to predict when the blue car will catch the white car in this situation. The situation is, since the white car is a little slower, it has a velocity of 1.58 meters per second. The blue car has a velocity of 1.82 meters per second. We're going to give the white car a 1 meter head start. How far down the track will the blue car catch the white car? I wonder. Let's think about the equation y equals mx plus b. Now that's the line equation, right? Well, if we're graphing a distance over time graph, right? We use x for distance, but if we're using the distance over time graph, we can make a line like this and then a line like this. Now this first line is the white car starting at t equals 0. And the second line is the blue car starting a little bit later. Okay, now this wouldn't be the right graph for us. Since in this problem, the white car is going to have a 1 meter head start. If this is distance, and I'm using an x to mean distance, and this is time, then the white car is slower. It's going to have a 1 meter head start. It's going to start here. And then the other car will start at, we'll call that t equals 0, later. Does that make sense? So this is the white car, and this steeper line is the blue car. So if these are meters here, 1, 2, 3, 4, and this is time going by, we understand that this is what our graph is going to look like. It's not going to look like this. This graph is a car that starts 1 second later. This graph is a car that has a 1 meter head start. See the difference? These two formulas are exactly the same thing. Y equals mx plus b, that's the line formula. Well, if we're graphing distance over time, and the slope of this line is equal to velocity, like we know it is, then these two are the same formula. This formula is in your physics tables. xf equals vt, and this little bar over the t means the velocity is constant, plus xi. All right? So xf equals vt plus xi. Let's put some numbers in right here for the blue car. The blue car goes 1.82 meters per second. So we could say xf equals v, 1.82 meters per second times a certain amount of time, plus 0, because the blue car does not have a head start. So the distance the blue car will go on will be equal to 1.82 t. Now, we could graph that on a graph. Over here, let's talk about the white car. xf is equal to vt. The velocity of the white car is 1.58 meters per second. T is the amount of time. And guess what? The white car has a 1 meter head start. So having a 1 meter head start and being slower means that its line is going to be a little bit flatter, and it's going to start up here at 1 meter. Here's our time going by. All right, now how could we figure out where these lines cross? This is where the cars pass each other. We can take these two formulas. See how they're both equal to xf? This is the xf point right here. So let's just set these two equal to each other. What do you mean, Mr. Perkins? I'll show you. 1.82t equals 1.58t plus 1. I take this formula, and I put it right there, put that formula, and I put it right there. Let's solve this using Algebra 1. 1.82t minus 1.58t equals 1. 0.82 minus 0.58, 1.82t minus 1.58t gives us 0.24t equals 1. All right? And then we'll say 1 divided by 0.24. That's going to give us just a little bit over 4 seconds. It's going to be right at 4.2 seconds. Okay, so how could we figure out how far down the track this collision occurred? We can just take this 0.42 seconds, 4.2 seconds, and insert that for t in either equation. So we have either 1.82t, that's the distance the blue car went, or 1.58t plus 1. These will both give you the same answer. So let's just put the 4.2 seconds into this equation. 1.82 meters per second for 4.2 seconds. How far down the track? Times 1.82 equals. There should be a collision about 7.6 meters or so, I'm rounding, down the track. Let's take a video of this. Okay, I use this meter stick. And starting at the red and white line, I marked down the hall our distance. Right here, I put a little graduated cylinder, the correct distance. This is where we would expect the pass to occur. Now let's film the two cars racing. Okay, this is the blue car. If you watch the video, I'm going to start the blue car after the white car has already traveled for 1 meter, okay? So keep that in mind. All right, here we go. We might get it on the first try. We don't know. These cars are hard to drive. All right, let it rip. Oh, perfect. We're very close either way. That was pretty close. We're having a hard time driving the car straight because they're not very high quality cars. We're going to try one more for you. Now remember, this graduated cylinder is where we would expect the two cars to be at the same place at the same time. Mr. Shosek's going to walk behind the car so he can drive it better. It's a really cheap car and it doesn't have a very long range, okay? So we're about to let it roll. Here we go. That's it. Okay. Disconnect. Hang on, I have to reconnect it. I can't edit this, so you got to hang on. All right, here we go again. Remember, the white car or the white and black car is going to have a 1 meter head start before the blue car starts. Here we go. This is the part where I smashed this car because it stopped working in the middle of the lab. We're going to have to go with the first run.